This simple piece of stone can illuminate a city for a few years. Again, it is possible to erase the city from the map of the world with this same stone. The name of this wonderful but terrible stone is uranium. Once used only in glass containers, this uranium is a symbol of power in the present world. Because it can be used to generate electricity and also to make terrible bombs like atomic bombs. Today's video is about how people discovered this uranium and how energy is obtained from uranium. The credit for the discovery of uranium goes to the German chemist Martin Heinrich Klubb. He was experimenting with a black stone or mineral called pitch blunt in 1789. At that time, this stone was thought to be an ore of iron and zinc. Klubb first dissolved pitch blunt in nitric acid. German chemist Martin Heinrich Klubb in the pitch blunt dissolved a strange liquid from a mineral and carefully removed its impurities. After adding potash, a yellow substance settled at the bottom of the container. He separated this yellow deposit and heated it with carbon, producing a black, shiny powder unlike any known metal of the time. Klaproth realized that this mysterious material behaved very differently from metals like iron or zinc, leading him to believe he had discovered a completely new element. Just a few years earlier, in 1781, astronomer William Herschel had discovered the planet Uranus. Inspired by that groundbreaking discovery, Klaproth named his new element uranium. However, there was one problem: he had not actually produced pure uranium metal. The black shiny substance he created was later found to be uranium oxide, a fact scientists would only uncover 52 years later. In 1841, French chemist Eugene Melchior Polygore was the first to suggest that the substance in the club was not pure uranium but uranium oxide. Polygore was also the first to isolate pure uranium. Polygore realized that it was not possible to remove oxygen from uranium oxide by ordinary combustion. As a result, he adopted a different method. First, he added chlorine to uranium oxide. In this, uranium reacted with chlorine to form uranium tetrachloride, which looked like green crystals. Then Polygore heated uranium tetrachloride and pure potassium together in an iron vessel with air. In this, potassium reacted with chlorine and uranium to form potassium chloride. As a result, pure uranium was released, which looked like a silvery white color. That is, pure uranium metal looks like a silvery white color. Until then, people had no idea about the capabilities of uranium. Uranium had no special use except for its use in glass containers. When uranium was used in glass containers, the glass containers would glow bright green in ultraviolet light, which would free people. As a result, the use of uranium was limited to enhancing the beauty of glassware. The potential of uranium began to be revealed about 100 years after its discovery. In 1896, French scientist Henri Becquerel discovered that uranium emits invisible rays, which create black marks on photographic plates, which we now call radioactivity. Becquerel's discovery of radioactivity happened somewhat by chance. As a result, this matter is known as one of the greatest accidents in history. After the discovery of Röntgen X-rays in 1895, this observation led Henri Becquerel to believe that when X-rays were emitted from a cathode emit energy, a bright such as uranium compounds is created, might also be capable of producing X-rays. To test this theory, he planned an experiment using uranium salts exposed to sunlight. He expected the salts to absorb the sunlight and then release X-rays. For the experiment, Becquerel selected uranium potassium sulfate. Everything was prepared on February 26 and 27, 1896. However, the weather turned cloudy, and without sunlight, the experiment could not proceed as planned. Disappointed, Becquerel decided to postpone the test. He then placed the uranium salt along with a photographic plate wrapped in black paper inside a drawer, intending to continue the experiment later. On March 1, Henri Becquerel decided to continue his experiment. Before exposing the uranium salt to sunlight, he developed the photographic plate that had been left inside the drawer. To his surprise, the plate showed a strong dark image created by the uranium salt. Even though it had been kept in complete darkness, this remarkable result revealed that uranium was emitting a powerful invisible radiation capable of passing through black paper without any help from sunlight. Becquerel called these mysterious emissions Becquerel rays. Later, Marie Curie and Pierre Curie studied the phenomenon in greater detail and introduced the term radioactivity to describe the spontaneous emission of this invisible radiation. Marie Curie eventually proved that uranium's radioactivity was not caused by chemical reactions or external conditions. Instead, it was a natural and intrinsic property of the element itself. In addition, the Curie couple noticed a strange thing while experimenting with pitchblende, and that is that the radioactivity emitted from pitchblende is much higher than the radioactivity emitted from pure uranium. As a result, they realized that there are things hidden behind the uranium in pitchblende that are several 100,000 times more radioactive than uranium, and these hidden elements were polonium and radium, which were discovered by the Curie couple. Finding these elements was not easy at all, because the amount of these elements in pitchblende was so low that it can be compared to finding a needle in the sand of the sea. The Curie couple was able to separate only 0.1 grams of radium chloride from several tons of ore in 3 years of effort. The Curie couple's contribution to understanding radioactivity is outstanding. Then in 1932, British physicist James Chadwick discovered the neutron. This opened the door to nuclear energy. Scientists observed that an element was being hit by a neutron and converted into a heavier element. That is, when a neutron hits an element, the element absorbs the neutron and converts into a heavier element. In December 1938, Otto Hahn and his assistant Stresemann were doing the same work in the Berlin lab. They were using uranium as the element. They thought that uranium would absorb neutrons and transform into heavy elements. After this incident, Otto Hahn wrote in his diary, "As a chemist, I have to say that it is no heavy elements were formed there. But according to physics, this is impossible. An element called barium was formed. The breaking of uranium into barium its atomic means the mass nucleus is about of the atom bursting, uranium, which had never been thought of before." Otto Hahn communicated the results of his experiment to Lisa Meitner in a letter. Lisa Meitner, with the help of her nephew, Otto, calculated that the nucleus of uranium split into two parts when hit by neutrons and that some mass was converted into energy during this division. They called this process nuclear fission. Before Hahn and Stresemann's experiments, people believed that the atom was indestructible, but they proved by hand that atoms can be artificially split. When an atom is split, it is converted into another element and a large amount of energy is released from this split. For this contribution, Otto Hahn was awarded the Nobel Prize in Chemistry in 1944. The immense power of uranium was revealed through nuclear fission, the result of which is so much discussion about uranium at present. In the ore of uranium that is found, 3 types of uranium are mixed: uranium-234, 235, and 238. Now the question is that the element is the same, but there are 3 types. What does this matter? The number of protons in each of the 3 types of uranium is 92. But the number of neutrons is different. For example, uranium-234 has 92 protons. The number of neutrons is 142, the sum of which is 234. That is why it is uranium-234. Uranium-235 has 92 protons and 143 neutrons. Among the 3 isotopes of uranium, the mass of 234 is very slightly less than that of 235. At the same time, the mass of 235 is very slightly less than that of 238. That means that it is the same metal, but the atomic mass varies according to the type of isotope. In nature, the amount of uranium-238 among these 3 types of uranium is 99.27%. The amount of uranium-235 is only 0.72%, and the amount of uranium-234 is almost zero, only 0.005%. Now, out of these, uranium-235 is required for nuclear energy. During this process, a massive amount of heat energy is released along with additional neutrons, creating a controlled chain reaction inside nuclear reactors. This heat is then used to produce steam, which drives turbines to generate electricity. Due to its efficiency, stability, and comparatively manageable properties, uranium-235 has become the primary fuel used in nuclear power plants around the world.